Okay, guys, just realized that I in between the breaks, I mean, in the during the break, I check if there's something wrong with the video, and I don't know why Zoom does it, but Zoom puts with the video sometimes floating, sometimes next to the screen because there's a click, there's a button for it. I didn't choose it, but sometimes my video is floating. Sometimes it's just stitched to the corner, and I thought that it was floating and it was stitched to the corner. And the funny thing is, in the video, when I was talking about this guy, guys, I was saying there's a famous blow from. It was so funny because I've got my video there, so it's like I'm talking about myself. I was not definitely not talking about myself. So it is this guy's blog, and the YouTube video is at, and the link to a YouTube video is also at the website, which is this. Okay, so I'm going to make the screen big again, and you're going to lose his picture. Okay. Okay, so good. I'm glad that we had this explanation. Okay, so we were saying that we were talking about the input gate, we were talking about the forget gate, how it forgot and how it was all vectoral. And since the multiplications are element-wise, actually, it is not you totally forget it or totally keep it or totally just lose some of it. You have a vectoral representation in some dimensions. You forget it in some dimensions, you don't. So each dimension represents another part of the state. Actually, those dimensions create multi-states, if that's the proper way to put it. Okay, so guys, that was the input gate. And next one, we have the input gates, which is called the input gate. Because actually we do the 10H operation here. We just convolve the gate with the input value, and you have the hidden state and the input value concatenated here. It is being fed to the tangent gate just like the RNN. So it is, this part is just like the RNN. At the output, you have the output of the hidden state. So it is like, if this is the analogy, at this point, actually, you have something like a next when you compare it to the RNN, okay? So you're convolving the input with the hidden states to create a kind of next state, which is not next because it's also intermediate at this point. And you, by using a gate, you're adding a part of it to the cell state. So it is like you're adding the inputs effect to the cell state. I don't know if it was forgotten here. I don't know if it was kept the same, but the effect is being added again by using the input. Because if these are all zeros, nothing new from the input is being added. So that part of that element of the sequence was like noise for the network. I just don't get any information. So let me not change my cell states, it is saying. Or if it is one, you're adding very powerful part, you're adding a powerful signal to the cell state. And you're relating the hidden states, which is the short-term memory, to the long-term memory. So it is like you're learning something very new and you're just adding it, you're embedding it into your long-term memory. You're just fusing them. So the input gate does two things. Passes the previous and hidden state and current input to a sigmoid function that decides if the value is going to be updated. And it decides what is to be passed using the tangent function. And since it's the tangent function, it is regularized between -1 and +1. So it is like a kind of intermediate hidden next state. And whether if we are going to just add it to the cell state or not. It makes sense, right? If you analyze this LSTM further, you just see that it has been, purposefully designed. I mean, definitely is purposefully designed, and it's a very such nice design. You can forget something, or you can just update it by using the current information if you need to, and it's going to be decided by the gates themselves again. And at the end, we are going to use the cell state to create the next input, the next hidden state. Good. So at this point, guys, we have forgotten some part of it, we have kept some part of it, and we have updated some part of it, maybe the same part, some other part, because these are all element-wise operations. And at this point, I have the new cell state. because that makes sense. Because the new cell state is either it's reset, or it is the same, or it's updated a bit using the inputs, the new information. So this is the cell state. So at the output of the input gate, we have the new cell state. We still don't have the new hidden state. So we have the long-term memory at this point, because this input, it flows like this. So at this point, I have the output, the cell state, the next cell state. Good, good. So the sigmoid decides if it's going to be updated or not. I guess that's pretty clear. So if you get to the formulation, actually, we have something like the input fuzzy gate, which I call ICAP. So input fuzzy gate, these are just 0, 0.1, 1, 0.9, some fuzzy logic values between 0 and 1, because this is, as you know, between 0 and 1, because it's a sigmoid. So this is the value. And I'm using this value to update in an element-wise manner. This guy. So this is it. So I've concatenated the input and the previous hidden state, and I've just fed them to this sigmoid. It is here. And by using the weights inside it, this is the weights in the first input sigmoid layer. This is the sigmoids. And because this is sigmoid, I'm using the sigmoid side. I have the intermediate fuzzy logic input gates values here. Then I'm calculating the what I called the intermediate hidden state, next hidden state, which you can see here. So is this formulation correct? Yes. Well, actually, this is there's something missing here. So I guess I should have this here as well, which is simply this. Okay. So the next state is, this is like this point. So before I edit it, it's a cap. And when I add this cap thing to the updated one, which was C cap, remember, so C tilde plus C cap, C tilde plus C cap is C next, which is this. Okay. So be careful. This is, so I forgot it. This is this, guys. Okay. This is how we do it mathematically. Good. So as you can see, the next state is, this is wrong, guys. Yes, this is I, and actually, yes. Yeah, what I thought of in the slide C cap as being this point, but it is wrong. I mean, yes, it is. In this slide is, maybe I should put it that way, guys. I don't want to confuse you, because I got confused. I'm going to just say it again. So actually, guys, this is here, not here. So I call this one. So these are being multiplied in an element-wise manner. So this is again connected to here, not here. And when you multiply them and just add them here, you have the cell state. Okay, and what we do at the final gate, the output gate. Actually, the output gate is not the output as you know it. The output is of your design. The LSTM has nothing to do with your output. LSTM only cares about the cell state and the hidden state, its own states. So it's a pure recurrent architecture. It doesn't have the output, additive output layer. You may edit you may add an output layer which takes into consideration of the cell state or hidden state or of your design. Some of them, I don't care. But this doesn't have the actual output of your application. The output, so-called output gate or the LSTM, actually feeds out the next hidden state, the short-term memory. And actually, it's very simple. You fed the inputs, you have concatenated them here, which is this one, and you just transferred it to here. There's a gate here as well, which is the output gate. You've got some fuzzy values, and those fuzzy values are element-wise multiplied with the current cell state. So actually, each next hidden state is calculated as a function of the new cell state and a fuzzy gate, which was calculated from the previous hidden state and the input. Actually, this also makes sense, because the next hidden state should relate to the current state of the network. And we are doing it by having a gate here, which is being multiplied by the hidden cell state. Okay? And if we have done this thought experiment before. If you look at it, for the cell state, we have the highway, so the gradients can pass if they need to, but we don't have the highway for this. That's why this is for the short-term memory, and this is for the long-term memory. And these are the functions, guys. These are very simple. I mean, when you just unroll them, the functions, the networks become much complexer. But when you put it on figures like this and just name each of them, they make sense and they're actually very simple. Okay, this was the LSTM input output. Let's make some observations. Actually, I've done them, I mean, instinctively when I was talking about the slides, but I'm going to go over the paragraphs in the slides and we are going to do them again. So during backprobe through time, for the cell state, there's always an open highway. We could just, so that's why it can keep long-term memory dependencies and long-term memory. And during backpropagation through time, for the hidden states, the road could be congested. So it is like this guy is taking the highway, but this guy is taking those small roads in between some streets, and it may get congested and it may stop and we may lose him. And that's the short-term memory. The car that drives slow and the car that drives fast. So that's why this is called the long short-term memory. Guys, first, any questions about LSTM mechanism? Because there's nothing more to it. I mean, there is no technical or something mechanism-wise we can learn from it. It's an RNN combined with some fuzzy gate mechanisms, nothing else. And it magically works. Any questions? Again, it is either very late or everybody is very tired or you're getting it very good. Good, guys. So the LSTM was fantastic and it was in 1997. And by the way, guys, there's a funny story of Schmidhuber. Did I tell you this in these slides? If I did, because they're on YouTube, I'm going to look like an old man, whatever. In 2016, he makes this speech and he says, he talks about Schmidhuber, recurrent neural network, the history of recurrent neural networks. It's a symposium in NeurIPS, that conference. Please watch that. He's very good. And here he just confesses that to everyone. LSTM, when applied for that conference in 1996, was rejected because it is so recent that we have come to the quite understanding of LSTMs and how fantastic they are, and they are being used widely. LSTM is, in everyday Google, you're using an LSTM. The way Google finishes your words is actually no different than the example we have covered the previous week, the live code example. It is not a vanilla RNN, it's an LSTM. And for each user, for each Gmail user, Google user, there is a separate LSTM. They are keeping your LSTM weights somewhere in their servers. And each time you're just typing something, the words are being refreshed according to your LSTM weights, guys. That's simple. So it's everywhere. LSTM is like a de facto standard. It's like so, I mean, something very fundamental in nowadays world. And GRU is was proposed in 2014. So it is like LSTM remastered. However, it is LSTM remastered definitely, but today's nobody can come up to a decision like, or LSTM is better or GRU is better. There are applications where they test it and GRU gives slightly better results, and there are some applications they tested and LSTM gives slightly better results. And since these guys are not totally transparent systems, you're getting big data and training them, and after training you got some results, and it is very difficult to make sense of why GRU gets a slightly better result. Whatever, it's by maybe chance because of the training, but you don't know. It's not transparent most of the time. But what we know is their performance is very similar. But traditionally, usually LSTMs are slightly, preferred. However, the main purpose of the GRU was efficiency. So we are, providing a version which is slightly, which is the same, let's say, because there's no study that definitely says this one is better than the other one always. So you don't know which one is better. They're quite the same. But it was designed to be more efficient because it has less gates, guys. Less gates means less operations. And when you have less operations, you can just embed them in edge systems or embedded systems, or by using less computational power, you can use them. It has two gates, sigmoid, and a single tangent. If you make the comparison, that's definitely something, right? It's just like the half, not totally half, but like half of computation you do on the other side. There is no output gate, guys, because, wait for it, GRU doesn't have a separate cell state and a hidden state. It has a single fused state. And in that fused state, both the long-term and short-term information is kept. Well, it makes sense because actually this is a state vector. And in this state vector, we have so many elements. Maybe one element is keeping the long-term memory thing for something, and maybe the other one is keeping the short-term memory. So it's fused. When designing GRU, the idea was we don't need to make separate long-term, short-term states. Let's fuse them. This system is totally not non-transparent. Why try to make long-term and short-term separate to make it somewhat a little transparent? What's the reason of it? So that was the idea, and they come up with this idea, and it worked. It definitely worked. So reset and update gates basically do the same thing as LSTMs. You have a state. You can either reset it, you can make it zeros, some parts zero, slightly make it zero, just playing it with its gain, so just lower the gain of that element, or keep it the same, because this is a sigmoid, it could be one as well. Or when you do it, depending on the input and the previous state, I'm not saying hidden state or cell state, this state, just update it a bit, update a part of it. And I'm going to go over the formulation because it's so simple. Go over the formulation on your own, because this depiction, this figure has it all. This gate updates, resets it or not. And this one creates a gate which you invert. This is negation. This is like a NOT gate. Sorry. This is like a NOT gate. So whatever value you have, when you just multiply it by 1, so it's 0, 1, 0, 9, 0, 3, 1. So when you update it, so negate it, so 0, 9, 0, 1, 0, 7, 0 kind of. So it's like negation gate, edit, and it's being updated by multiplication this time, and you add the value. So every mechanism exists, but they're all fused in a single state. Less gates, less states, more efficiency. Okay. So LSTM is in some sense more transparent, because for the long-term dependencies, we have the cell state separately. But for GRU, we have a fused state vector where all short-term and long-term dependencies exist together. Okay. 3 nonlinear activation functions versus 5 nonlinear activation functions, which is quite a difference. And it's like double the calculations. But we don't know how many vectors you're going to use. Maybe for a similar performing GRU, you will have a longer state, because a state vector, because this is the combination of them. So we still don't know how much exactly calculations how much calculation does it exactly do inside, because it depends on the vector size. So if the vector size is the double size, so it's going to make so many. So we just don't know, but it is designed to be more efficient if it can be. So it's an hyperparameter. So you may ask, how am I going to select the number of vectors or the parameters? Well, that's a hyperparameter search. Do a hyperparameter search and just decide, do an automatic hyperparameter search using neural search algorithms, or do it on your own manually. Doesn't matter. This is an hyperparameter. And in practice, as I just said, literature shows that they perform similar. And actually, they are not the only two types of recurrent cells. Next week, I'm going to be covering different variants of LSTMs and ideas on LSTMs, different ideas to make these mechanisms more, I don't know, effective in some applications. However, GRU and LSTM are like the kings. I mean, if you're going to do something, these two you definitely should try first. And there are others as well, and we are going to discuss them next week. And their comparison is a detailed subject, and their comparison is already done, which we are going to be discussing in detail next week. And I just, in anyways, if you're interested, if you want to take a look at it before next week, I've just put the link to it on the suggested reading and here as well. So it is. So one of the authors are Bengio, I don't know how it's pronounced. It is one of the famous guys. So they've done a nice analysis between LSTM and GRUs and how they function and what is the best site. So empirical evaluation of gated recurrent neural networks on sequence modeling. On different basic and complex sequence modeling problems, they tested. They do a controlled experiment. And here's the link. Here's the blog discussing that discussion, because there's something nice with this in towards data science and machine learning blogs. They do this. There's a paper, and people read that paper and they discuss it in the blog, and they are very, 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 useful. Please do that. Okay, okay. Here's the suggested reading. And next week we are going to cover different types of LSTMs, different types of also be the BLSTM, which is more important, and maybe some live coding. I say maybe because next week I'll be moving from one university to another university. I'm not sure how comfortable I'm going to be. So if not next week, it's going to be the other week. Okay. Any questions? Okay. 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 Okay then.